So hello again. This video will show how to implement the Newton-Raphson method, again, to solve a small problem. So here again, I'm importing from the SymPy library, symbols, function, differentiation, and evaluation. And I will use also an import from NumPy, the linear algebra package. So here I define x1, x2 as my symbols, which are my variables. The function f who takes two variables x1, x2, and basically in my example, f is equal to x1 minus 2 squared plus x1 minus 2 x2 squared. So I'll display f, I'll compute the first partial derivatives respectively with respect to x1 and x2, and I will also need to compute the second partial derivatives with respect to x1, x2, which is basically also the same the second partial derivative with respect to x2, x1, and finally with respect to x2 twice. And I'll display these second derivatives here as you see it. Now I will go to the main algorithm. Well, all I need here is to define a list of x1 and x2 values, which will be updated for every iteration. And I will initialize here. I will start from the point 1, 1. Okay. And for the main loop, I will iterate going from 0 to 10. So I'll assume that the maximum number of iteration here is 10, but you'll see that it go very fast. So beginning of the loop, I will evaluate the first partial derivatives. I'll substitute in fx1 and fx2 with the current values of x1 and x2 and evaluate. I will compute the gradient. So the gradient to me takes the float of f1, the float of f2. And I need this to update the values of x1 and x2. I'll compute the second partial derivatives and evaluate them. So I'll substitute with the current values of x1 and x2, as you see. And I will enter this in the Hessian matrix, which takes the floats of these values also. I'll display the Hessian matrix. I'll invert it using the linear algebra package. And all I need now is to compute how much is the H1 inverse times the gradient of f at the current xk. So I'll say that S is the dot product of the inverse of H by the gradient of f. And I will use this S I obtained to update the current value of x. So the x, or the current point of the current solution, to me is going to be an area of x1i, x2i minus s. This way it has been updated, and I will give to x1 at I plus 1, next position, x2 x at I plus 1, the entries at 0, 0, and 1, 0, because x here is basically a 2 rows, 1 column matrix. So this way it works quite fine. And you'll see how it iterates, and at the end I'll display the final solution. So at the beginning of the algorithm, you see I'm displaying here the Hessian matrix. I'm inverting it, and this is the S after the multiplication by of S by the gradient, and the current solution I obtain after just the first iteration, since I started from 1, 1, is from 1, 1 is going to be 2, 1. Okay, which, as you know, is going to be the final solution. So the remaining iterations are useless, in fact, and this is the final solution, as you see. Okay, and if you compare this video with the previous video, you see that this allows us to go much faster to the final solution compared to the steepest descent method. So that's it. Thank you very much. I hope this helps.